Hi, in this video we are going to be talking about Unreal Engine's Blueprint scripting system. Blueprints are a visual scripting language and the tools that come with it that you will run into pretty much throughout the whole engine. It is used from gameplay and level scripting to creating animations and sound systems and interactable objects, as well as player characters themselves, and even UI logic, as well as editor and automation tools inside Unreal. It is very similar to the underlying C++ code and the hierarchy that is made up of it. In larger projects, usually both C++ as well as Blueprint scripting are used, but many games are wholly done in Blueprints themselves. When using Blueprints, you will be taking a speed penalty. The severity depends on the kind of code you are writing in it. If dealing with simple if this then that statements that only affect a few actors in the world, it probably won't be huge. But if you are dealing with many hundreds or thousands of objects, then that type of code would be more suited for C++. All of this said, Blueprint code can be nativized, and it is really fast for prototyping any kind of functionality, as well as ideal for level scripting, because it is so modular and recompiling blueprints is a lot faster than C++ code. We are only going to be scratching the surface of what blueprints can do in this video. So if you want to learn more, check out the documentation as well as the content examples project and all the blueprint-oriented examples inside it. We are going to be working on the controlled lander task. This is the first task that uses a base project, so download it and extract it to a sensible place. I have already done it, so let's open it up. Note that there is no saved or intermediate folders included in this project. You don't need to include them either when you are submitting your work. We can launch the project by double-clicking the uProject file. Because this project was built with an older version of Unreal Engine, I am asked which version I want to update it to. In my case, the latest stable version is the version 4.23, so I'm going to be using that. Click OK. Now with the project loaded, let's check out what is going on here. This is a template for a simple Moonlander style game. And when I go into game, I have my spaceship, but it is falling down and exploding. So let's try to actually make it controllable. The end goal of the ship would be to fly from the start location to the end location and land on this platform here. Also note that the game world is constrained to the ZY plane. Content-wise, there is very little content in the project. You can check it out, but the folder we are most interested in is the Blueprints folder. There are two classes here, the game mode class as well as the actual player pawn class, which is called the Blueprint Player Lander. To see what the hierarchy of the objects look like, let's open up the new Blueprint wizard. In here we can create a new class, and this class can be based on any of the classes that already exist inside the engine. Actors are objects that can have some logic attached to them. Pawns are actors that can be possessed by either players or AI. Characters are pawns that have extra functionality built into them, like a collision mesh, as well as the visible skeletal mesh, but most importantly the character movement component. Then we have the player controller, which is an actor responsible for actually controlling the pawn. Then we have the game mode. Here you should store all the logic that pertains to the actual game type and its rule set. Inside actors and pawns, you can have many components. You can have components that do not have a transform, or you can have components that can be attached to other components and have an actual transform. These are the most common classes, but if you want to, you can take a look at the whole hierarchy that you can use as a base for your own custom classes. Let's take a quick look into the actor class. In here you can see all the classes that inherit from the actor class itself, including the pawn class, and more specifically the actual player lander template class that was created for you. What you see inside the game world is not the classes but instances of objects created based on those classes. So I can add an instance of the player lander here in the game world. And you can see its type is Blueprint Player Lander. As an instance of the player pawn is spawned when I actually jump into the game, I don't really need the second ship here, so I will be getting rid of it. Most of the changes we are going to be making are going to be living inside the lander class here. So let's open it up for editing. Let's go over what we can see here. On the top here is the main toolbar where you can compile and save your blueprint, as well as simulate it locally. And you can also launch a play and editor session from here as well. On the bottom left here is the My Blueprint section. In here you have access to all the components, which you can also see on the top left here. All the variables, functions and graphs that make up this specific blueprint. On the right here we have the details panel, which gives you access to the currently selected object. In the middle here is the actual work area that can display the graphs, or functions or macros for that matter. And in the viewport you have a visual representation of this blueprint. Let's go over the components that make it up. We have the hull mesh, we have the leg meshes, we have the camera, and we have particle effects for the thruster, as well as an explosion particle effect that is not enabled by default. Now on to actually making it fly. For that, let's first off, just because it's a bit of a distraction right now, let's disable the thruster particle effect. For that, select the effect. In its details panel, scroll down to the activation section and untick the auto active flag. Now when we jump in game, we can see that the thruster effect is no longer active. There are many ways in which we could make this ship move. We could directly modify its position, we could add a movement component to it, or we could modify its physical state with forces enacted on it. As said in the task description, we will be using the last method. So how will this work? We have the hull mesh, which is a static mesh, and it has a bunch of properties to it, one of which is its physical state. It is set to simulate physics. So if I unticked this flag here and went into the game, we can see that the ship no longer falls down, which is nice, but if we added any forces to it, it wouldn't do anything. So let's re-enable simulate physics. We could also disable gravity, but that would be cheating as well. When talking about adding a force via a function, let's see how that would work. Let's navigate into the event graph. Let's grab a reference to our hull mesh. Let's see what we can do by clicking and dragging on this pin here. Once we let go of left shift, we are presented with a search menu. We could go through all the options here and see all the kind of functions and things that are available to us, which I do recommend you do to know the things that are available to you. Although do note that this is context sensitive, but in this case let's use the search functionality, as it is really powerful and it will probably make it easier for us to find what we are looking for. For that, let's search for force. In here we have many options, but let's select the simplest one of add force. Now we added an add force function, which is represented as a node that has a bunch more pins on it. Right now the force that is added is 000. Let's make our ship fly upwards. For that, let's modify the z value here. As Unreal units are centimeters, we will want to insert the Greek value here. Let's jump in game and see what happens. Still nothing, our ship still falls to the ground. This is because the function itself is not executed. This is the execute pin here. To make it execute, we have to add input from somewhere. In this case, let's use the event tick node. The tick event is an event that is triggered each frame. So each frame we are sending an execution order to add this huge force. Let's see what happens now. Because the force was so huge, we flew into space. What we could do is tone down the force. Let's ignore the warnings for now because they are caused by our ship moving really fast, really far and messing with the physics system. So let's actually tone down the amount of force we are adding. This is somewhat more reasonable. Now we do have our ship flying upwards, but wouldn't it be a lot nicer if we actually had a specific thruster component that would do this for us? And actually there is one. So let's actually exit out of the game mode and get rid of this add force function. Let's go into the viewport, so we have a better view of what is actually going on here. To add a new component to our blueprint, let's click the green add component button and search for a thruster component. We can see that there is indeed a physics thruster component. Looking at the tooltip, we can see how the component works and that the force is applied down the negative x direction of this component. This will become important in just a minute. For now, let's add the component by clicking on it. The name physics thruster is fine. Now let's move it down a little bit so that we can actually see what is going on. It was said that the thrust was applied down the negative x-axis. So let's orient the component. For that, let's go into orient mode with E and make the positive x-axis point down. To see that we oriented it correctly, let's go back into the translate mode. And we can see that the red x-axis is pointing straight down. In this component's details section, let's increase the thrust strength. Again, let's go a bit overboard at the start. And also make it auto-active, meaning that the thrust is applied as soon as the game is started. If this is left unticked, nothing happens until the component is specifically activated. So let's tick this, and now jump in game. Again, the force was too large, so let's tone it down a little bit. And try again. Now this looks somewhat similar, but indeed it is a little bit different. This works like an actual physical force. To demonstrate that, let's take a look at our ship. And let's move the thruster to the left, for example. Which makes sense because we are applying the force off axis. Now when we jump in game, our ship starts spinning rapidly. So indeed this thruster acts more or less like an actual physical thruster would. Let's move it back to the center on the y-axis. As it works like an actual physical thruster, we can use an effect called thrust vectoring. How this works is that when we orient the thruster to one side or another side, our ship will start to tilt. To demonstrate that, let's orient the thruster a little bit to the left. Again, let's check the local orientation and let's start the game. You can see a similar effect as before. Let's do a little bit more groundwork before we can actually start controlling the ship with our inputs. For that, let's recenter the orientation of the thruster by pressing Ctrl Z. Let's add a visible representation for our thruster as well. For that, let's add a new component to our blueprint. This will be of the type static mesh, but because I already know that I want it to look like a cone, I can make my life easier by just searching for cone here. Let's add it and let's place it where the engine should be. Right now you can see that it was actually parented to the physics thruster. This happened because we had the physics thruster selected. And so the mesh itself was placed down here. In actuality, we want it to be the other way around, of our physics thruster being parented to the cone mesh. To reorganize this, click on the cone mesh and drop it on top of the hull mesh. You are given the option to either attach it or make it a new root object. We are going to attach it. Now let's reset its rotation. And let's move it upwards a little bit. This now looks a bit more like an engine would. Let's grab the physics thruster and let's parent it to the cone. Also, cone is a bad name, so let's name it something a little bit more proper. Engine mesh will do. Let's recheck that our physics thruster is still in the correct orientation, and indeed it is. While we have the thruster selected, let's also reduce the amount of thrust it produces. Removing another 0 seems to be a bit much, so let's just divide the currently entered value by 2. Now let's go back to the engine mesh. Let's scroll down a little bit to the collision section. Let's tick the simulation generates hit events flag. This is needed due to the way the explosion logic is set up. Let's add an arrow component to see where our engine is actually pointed. For that, let's add another component and search for arrow. Actually, before adding it, let's select the physics thruster and search for it again. Now by having the physics thruster selected, our arrow inherited its transform information. Let's make this arrow a bit bigger. And let's untick the hidden in game flag. Now when we go into game, we can see that there is this red arrow beneath our ship here. Now on to actually using keyboard input. What we could do is go into the event graph and add an input for key presses. We can right click anywhere in the graph here to bring up the search menu. You can see all the keys here as well as the any key option. I'm going to be adding the A key. You can recognize that this node is an event by the red color in its header. But if we constructed our input method by hard coding the input keys in the blueprint here, we would have a much harder time remapping them later on, as well as adding new input methods would be a lot more clunky as well. So let's get rid of it and do it in the proper way. For that, again, let's save everything. Let's navigate back to the level editor view. Let's go into project settings. Under settings, project settings. And let's go into the input section. We have a bunch of options here, but we care about the bindings menu. There are two types of mappings, action mappings and axis mappings. Action mappings generate events when a specific key is pressed, be it on your keyboard, on your mouse, gamepad or touch or whatever else. When compared to that, axis mappings are updated each frame and can have a multitude of values in a form of a float variable. To make the input methods the most versatile that they can be, let's use axis mappings because it will support analog input. If, for example, we wanted to add gamepad support later on. Let's add two axis mappings. Let's name them axis thrust and axis vectoring. For thrust, the mapping is simple. When we are holding down W, we want the thrust to be maximized, and when we let go of W, we want the thrust to end. So let's search for the W keyboard key and select it. But for vectoring, we will need two keys that will affect the axis value. One key to modify it in the positive direction and one key to modify it in the negative direction. So let's change this first scaling value here to be -1. This will be us turning left, so this will be the A key. And for turning right, we will use the D key. So for the axis vectoring value, when we are not pressing anything, the value will be 0. When we're holding down A, the value will be -1. And when we are holding down D, the value will be 1. And let's add in events corresponding to the axis mappings that we just created. For that, again, right click to search, type in thrust, and scroll up to axis mappings. We can either straight up get the axis thrust value float, or we can get the event as well. The event in this case fires each frame. We will be choosing the event option here. This added a new node to our graph. It has two outputs, the execution pin, which fires each frame, and the axis value. Before we forget, let's also add in the vectoring event. Again, right click and search for vectoring. If you named your axis differently, search for the name that you used there. Again, let's choose the event and let's move it down a little bit. So what we want is that when we are pressing W, we want our ship to fly forward. Now let's select our thruster. Let's disable the auto-active flag, meaning that by default, the thruster will be turned off. Let's drag in a reference for our thruster. And let's search for a way to change the active state. In this case, we want to set the isActive value. So each time the axis thrust value is updated, we want to update the active value. Once the execution flow here is connected, note that the floats are represented with the green color and Boolean values with the red color. Components are blue and transform values are orange. Back to the axis value. Like I said before, when W is pressed, the axis value will be 1, and when it is not pressed, the axis value will be 0. A lot of the useful basic math functions are built into blueprints. So let's search for greater. And let's use the greater option rather than the greater or equal than option. This node will output a Boolean value, which is either true or not, depending on if this A input here is greater than the second input here, which is a constant of 0 currently. So when the axis value is greater than 0, we want our thruster to be active, and when it is equal to 0, we want it to be inactive. Let's see if this works. When I'm pressing W, my ship flies up, and when I let go of W, it falls down, which is exactly what we wanted. Now onto the vectoring bit. For that, let's look at our ship. When we press the A key, we want our engine to turn to the left, and when we press the D key, we want our engine to turn right. To the right here in the details panel, we can see that the value that actually changes is this roll or X orientation value. Again. Let's go back to the event graph. We wanted to modify the rotation of the engine mesh, so let's drag a reference to it into the event graph. Again, search function is our friend here. Let's search for a rotation. There are a bunch of ways in which we can transform this component's rotation. What we want to do in this case is to set its relative rotation. And again, we want to update its value each time the axis value actually changes. So let's connect the execution flow here. Right now, we only care about this X or roll value here. To make inputting values here easier, let's split this struct pin and reveal the floats that make up the rotation value. We wanted to modify the X-axis by the axis value here. If we straight up plugged it in, it would update the rotation, but it would only do it by 1 degree. So instead, let's multiply this axis value. And let's plug that in instead. We might want to change the amount the engine rotates later. So instead of just entering a specific number here, let's actually promote this specific pin to a variable. We can do that by right-clicking on it and choosing the promote to variable option. This created a new float variable. Let's name it something sensible. Vectoring angle will do. This vectoring angle is a float which has a default value. But to see this value, we first need to compile the blueprint. Let's actually make this vectoring value a bit higher, 15 degrees for example. Now when I press A and D, the engine actually rotates, but it is inversed, so let's fix that. For that, we could either add another pin to this multiplication node here and make it -1, or we could change the vectoring angle to be negative, or update the input mappings themselves. I am a bit lazy, so I am just going to leave it like this. Now let's also fix the thruster effect that we disabled earlier. I'm just going to activate it for now to move it into place. This looks good. And let's go back to the event graph now. And because we already have our thrust value linked to setting the physics thruster active, what we can actually do is drag a reference for the particle effect and also reference it for setting it active as well. So in this case, we can actually have multiple references referencing this function at once. Now when I go in game and press W, the particle effect is enabled, and when I release W, the effect is disabled. Now that I can control the ship, seeing that the camera is parented to the ship's rotation is really disorienting, so let's fix that as well. Let's select our camera component and let's take a look at this transform section here. There are these down arrows next to the location, rotation and scale values. When you click on them, you can select this component's type. Is it happening relative to its parent, or is it happening relative to world? In this case, we want our camera rotation to be relative to world space. So let's choose that option instead. We can see that the value updated here. So now when we go in game, our ship rotates, but our camera stays level. In this case, I was lucky and all of this worked out for me. But if something went wrong, there are also several debugging options available in blueprints. First off, there are specific functions to print text to the log as well as on the screen. Here you have a string input and you can type anything that you want in here, as well as you can convert, for example, a float variable to string or a boolean or many of the other types that exist in the engine. In addition to printing debug text, you can also draw different types of geometry for debugging purposes. These are very useful for visualizing what your code is doing in the viewport. As another option to look at the values that are running through your graph, what you can do is add watches. Let's look at this multiplication node here. Let's right click on the output value and let's click on watch this value. When I now jump in game and for the debug object, I select the player lander blueprint, I can see that the axis events are triggering constantly. And when I move up a little bit, I can see that each time the ship hits the ground, I can see that the hit event triggers a bunch of other logic behind it. When you make the game viewport active, you can click Shift plus F1 to re-enable your mouse. Let's go back down to our vectoring event. And in here we can see that this float value is currently 0. Now when I press A and D, I can now actually see what is happening in the code. Breakpoints also exist. You can toggle them by pressing F9. And now when I jump in game and hit the surface, I can actually step through the code and see what is actually going on, each step at a time. We have one more issue. Our ship will not explode if it lands on this green finish tile here. To demonstrate it, let's move our starter location to the other side and let's go into game. To fix this, we'll need to edit our blueprint a little bit. Let's select our engine mesh and let's add an event for on component hit, which is the first one here. Let's move it up and let's connect it to this do once. So now if the hull mesh or if the engine mesh touch any sort of other surface, our ship will explode. Now that that is fixed, let's go back to the viewport and let's extend the landing legs. And now testing it in game. The ship doesn't explode because only the landing legs are touching the finish pad. The landing legs should only extend when there is a surface right beneath the rocket here. How to implement this I'm leaving up to you. But before I go, here are a few hints that will help you on the way. To make the ship sense the ground, you can use a function called line trace. What this line trace does is essentially send out the beam from the start location in world space to the end location in world space. And if it hits something on the way, you'll know about it and you'll know about its properties here. To figure out the start and end location, you can query the position of the blueprint. For example, by using the getActorLocation node. In addition, you can get the forward, up and right vectors to orient your trace. From here on out, you can use basic vector math. To make the lander legs animate, what we need to do is update their relative rotation, just like we did with the engine mesh. To make the process of animating itself easier, what we can use is a timeline component. Inside the timeline, you can add different tracks, for example, a float track to update the value. Back in the event graph, you can, for example, lerp the value between the actual rotation values that you want to use here. And you can use the output of this float to update the relative orientation of the legs. I'll leave the rest of figuring this stuff out up to you. Thank you.